Can you guys see my screen? Hello? Hello? Mm, Sanket, are you there? Hello, Sanket? Hello, can you guys see my screen? Hello? Uh, okay, so yesterday we stopped here. Uh, Before this, we converted our model to a TensorFlow Lite model using both quantization and without quantization. And we wanted to see if there's difference in accuracy of both the model. For that, we were writing this code, but we faced some error, if you remember. So I'll just explain this code once again. We Since now it's a TensorFlow Lite model, our Colab notebook won't be able to read it directly, so we'll need an interpreter for that. So first we made an interpreter, then we allocated some memory to both the models. Then to get index, we used get input details and get output details function to get details about the index. Then we made two arrays to store our predictions in that. After that, we used for loop to run our code through every input value, like, and then we converted our every input value again to TensorFlow model. After that, we predicted using sign model predictions and appended in the respective arrays. So now you can see the graph. All four graphs are almost overlapping to each other. Actual value, original predictions, then our converted sign model and converted sign quantized model. So as you can see, there's not much difference in accuracy. This is the thing we were trying to prove. And now we are seeing how much difference there is in size of all four models. See, why if you don't know why we need to quantize our model, because microcontrollers does not have that much space. So we need our model to be as much small as possible so we can like put it on a microcontroller and run our code. So we use operating system. This is a Python library or module. We use this to see size of our different models. So this was a basic model, and this is a quantized model size. For basic model size is 2736 bytes, and quantized model 2512 byte. You can see difference is 224 bytes. Then okay. Uh, by the way, these two cells of code we did not really need it. We did this to like prove a statement about quantized models. Then now this one is important. We need to convert a TensorFlow like that code in C code. For that, we need this code. So you don't need to like understand what this code means right now. You just need to copy paste it for now. Like, and if you like get too much interested in this TinyML, you can learn all this from internet. How to convert your code to a C code. Now this brings us to the main part of TinyML week, that is deploying a code on a microcontroller. Now Sanket will take us through this. So Sanket, can you take over?
I'm audible?
Uh, you can take over now. I said.
Yeah. Okay. Can someone confirm if they're able to see my screen?
Uh, okay, something is loading, I think. Or is it my internet
Okay.
connection?
Is my presentation visible? Hello.
Yeah, yeah, we can see your slides.
Okay. Okay, so hello everyone. Welcome to day four. Hello world of TinyML. We will continue. So now we'll be creating the TinyML application on Arduino IDE. So what have we done so far? We've understood the basics of TinyML, the flow of the program about quantization and flat buffer. We made the sine curve using TensorFlow, which was taken last session in the collab notebook by Santosh and Pratyush. So now, and we also generated a TensorFlow Lite model for microcontrollers using quantization because we need to do it because our microcontroller has limited RAM. So we need to decrease the space, optimize the space as much as possible. Generally, it is obviously due to loss of in the at the cost of accuracy. So we have to optimize how much accuracy we need and how much space we need to occupy. Okay, so that's what we covered so far. So now let's move forward. Now we shall deploy our optimized model. We'll program our microcontroller on Arduino IDE, build and upload a program to the microcontroller, and you will see that the brightness of our LED will change as per sine curve. Okay, so here the main thing is getting the sine curve, and then your application could be here application using a brightness of an LED. You can do many other things like use that for a buzzer and far much bigger circuits. But our motive here is to understand the basics of TinyML. So we'll just be doing adjusting the brightness of our LED. Okay, so for the following microcontrollers may be used. First off, with the Arduino Nano 33 BLE Sense, or SparkFun Edge, or ESP32. If you don't have either class, to listen. And I understand that not everyone will have hardware, so to do justice for that, at the end, I will turn on my video and show the demonstration in front of my webcam. So for today's demonstration, I'll be using an ESP32 Room 32E. It may vary a little, the code may vary a little for other microcontrollers, but the algorithm is more or less the same. Okay, so here's the circuit diagram. I think it should be pretty familiar with you guys because microcontrollers are already taken on week one. It's just an ESP32 and an LED on GPIO 25 pin, two resistors and grounded. Just a standard circuit of a blinking LED. Following that is the basic flow of a TinyML application. So you have three parts. One of them is a variables which will be put in the namespace, a setup function and loop function. I'll be going over each one of them later as we code along it. As of now, this is the whole picture. So the header files we'll be including is hashtag include TensorFlow Lite ESP32.h. So this library will allow you to run machine learning locally on your ESP32. So there's one more. You don't need to care about this path. You need to care about micro error reporter.h. So this line imports a class that can log errors and output and to help with debugging. So obviously you need to debug this thing. So we need an error reporter which will report errors when there's a problem. So which will help you to understand where is the cause of the bug. So then you have a micro interpreter. This library or the TensorFlow Lite for microcontroller interpreter, which will run our model. Then you need a resolver. So there are actually two types of resolvers. One is an all ops resolver that all the operations and micro mutable op resolver. So the first one imports the class that allows the interpreter to load all the operations available in TensorFlow Lite Micro. The second one, that micro mutable op resolver, allows the interpreter to load only the necessary operations used by our model. So in R, we'll be using an all ops resolver because micro mutable is a little complicated. But to make things simple, we'll be using an all ops resolver. There is a downside of all ops resolvers, which I'll be showing here. You can take a look. So a micro ops resolver, you have to connect to a built-in operator. The space it uses is 290,794 bytes. That's 22% of our program storage space. And when they compare to that, all of the solver, which uses all the operations, takes 28%. So obviously, if you had to pick, you would have to pick a micro observer because you want to minimize the space it takes, our program takes. So to keep things simple, here I'll be using all ops resolver. I hope that's clear. But then following that is micro ops at edge. This line is code all operation need by the resolver. And then you have something called schema generator. So this line of code imports the schema that defines the structure of the TensorFlow like flat buffer data, used to make sense of the model data in sign model data to edge. So we will be including sign model data. So we'll have to compare the versions if it's matching the schema generator. Otherwise, it will not run. So following that is version.h, which will just we'll have to compare the version of our model with if it's compatible for our ESP32. We'll be going over all of this in our code, so you'll understand better there. So before we start coding, a little speed of what we are to do here and see if it's way to increase by a resistance of the LED. Seem to be having network issues. Yeah. Can someone confirm we are able to see this video? Hello?
Yeah, we can.
Okay. Yeah, you have to. So I'll plot it and show that it's a sine curve later. But for now, you have to observe how the brightness is changing. That's all for
Sanket, your
IDE. Now
voice
let's
is
move on to
breaking.
Arduino IDE and make our own. Okay, I'll leave in a minute. Let's and make a very own tiny application.
Voice is not clear.
Sorry?
So voice is not clear.
Yeah, he's joining again. By the way. Yes, sorry, but there seems to be some issue with Cynthia. He'll rejoin in 1 or 2 minutes. So just wait till okay, join.
So is my voice clear now?
Yeah, yeah.
Okay. Okay, so this is our flow of a TinyML application. You're able to see my screen, right? Can someone confirm?
Yeah, we can.
Okay,
Now
so
we can.
I'll screenshot it to you guys.
We can see your screen.
Yeah, okay. So I took a screenshot of it and I will be editing it as we go. So I want you to all of you guys to open Arduino IDE. I hope all of you have it installed because we already finished week one. Tools Okay, so I want you to search TensorFlow on the library manager, and then there should be a library TensorFlow Lite ESP32. And I want you to select the version 0.9.0. Make sure to not select 1.0.0 because there recently been an update and it has been giving some problems. I want you to install 0.9.0 and install that library, TensorFlow Lite ESP32. So once you have the library installed, I want you to go to Files, go to Examples, and then I want you to scroll to the bottom. So there should be a tab Example from Custom Libraries, and there should be TensorFlow Lite ESP32. So in that, I want you to open the. Okay, so once you guys are in this tab, so let's start by killing all this code. We'll be making it all up ourselves and excluding the libraries because it'll take time to import the libraries. You can skip all of this.
So please repeat once
Be
again.
explaining how to go for all of it. Is everyone following up now?
Sanket, actually, someone said to repeat again.
Okay, so I want you to go to Tools, go to Manage Libraries, and once you open the library manager, I want you to search the tensor. Sorry for the delay. I'm having some network issues. So can someone confirm if they can see my screen?
Yeah, it's visible.
So okay, so now coming to LAN, I don't think I'll face any issues now. So I hope everyone was able to import the library and open Hello World. If not, I'm not sure when I was disconnected, but so do let me know if you're unable to reach the stage. All I wanted you to do is go to examples. There should be a TensorFlow Lite ESP32, and I want you to pick Hello World. That should open the sketch, and I want you to kill everything, kill all the code in under Hello World. I want you to only keep the libraries.
1 minute, Siddha.
So
Suresh, hello. 1 minute. Suresh, do you want to say something?
Yes, yes, please repeat. While explaining, he was disconnected. So please once, can you tell me which library I need to install?
TensorFlow, look, search up TensorFlow. So one of them will come
Ah,
TensorFlow Lite ESP32. I want you to install a
okay,
0.9.0 version. Don't install 1.0.0 version. There should be an option select version there. Choose 0.9.0.
okay, okay, okay. Thank you.
So once that is installed, go to files and go to examples.
Give them one or give them 1 or 2 minutes to install it.
Okay, I'll give you 2 minutes. Okay, so have you installed the library?
Yeah, yes, installed.
Yeah, so I want you to go to files and go to examples and then scroll to the bottom. Should see a library TensorFlow Lite ESP32. Then in that, I want you to pick Hello World. So once you have your Hello World open, I want you to kill all the code below. Only keep the libraries because we'll be hard coding all of that right now. So let me go over the other files here. So what I want you to see is sign model data.cpp. So this is our code here. This is our model. Just now we finished extracting the model sign model data.h from the collab notebook. So this is just that model. We don't have much time, so I couldn't cover all of this on my own. So I'm importing the standard one. So just this is the final C file which you'll be extracting from the collab notebook, which are already built in here in this example. So there's main function.h that just explains setup and loop. Nothing much to go over here. So this is our main code which we'll be coding now. Shall we start? So can someone confirm if my snipping tool is visible?
Yeah, yeah.
Okay, so let's see what we have. We have the variables, the sensor specific variable. We don't really have sensors here. We have model specific variables. So we need pointers for our model, our error reporter, input and output tensor, and interpreter. Let's start with that. So there's something called namespace, which is used to define models in C++. So to for a class, so when you're using our libraries, we the way we define pointer, we would do this tf light error reporter, and then we name it error reporter. For now, I'm just introducing to a null pointer. This is a standard keyword in C++. Null pointer just opens up a pointer of this type, tf light error reporter. So we have made a pointer to an error reporter. Next up, we have the model. Let's do the model. For that, we'll again make a null pointer. We'll call these pointers later. For them, I'm just creating the variable, creating the pointer. Sense? So then we have the input and output tensor and the interpreter. Let's do the interpreter first. Here it would be better to use a const because our model is a constant model pointer. Our input and output will keep changing, so it's better to use a constant pointer. TF light micro interpreter. We'll call it interpreter. So again, I'll just introduce to a null pointer. So we made a pointer to an interpreter. Now we have the input and output tensor. I'll do that too. So for now, we have to create a pointer of class TF light tensor. Again, I'll be introducing a null pointer. We'll call this pointers later and define them. For now, I'm just creating the variable under namespace. Okay, then. So now that does it. We've created our input tensor and our output tensor. So what we have next? We have to create a tensor arena. So we have to assign a size for a model. How much space we are assigning. The right amount is hard to say. It comes with trial and error only. So one more thing I want you to do is, so in our case, we are making an LED blink, right? So I've connected in my ESP32. I've assigned GPIO 25. So I think this should be familiar to you guys since we've already gone over microcontroller week. So now we close main space. So next up we have the tensor arena. So we have to create a size and an array. We have to assign the size and we have to make an array of that size. So we have to find the minimum value for a model, the right amount of space, because we want to minimize it, but we don't know how much. So it comes with trial and error only. So what we do is const expression and uh, k tensor arena size. So I'll be assigning it 2 into 1024. So we want to give it an 8 multiple because 1 bit is 8 bytes. We want to keep it an 8 multiple. And for this model, its idle value is 2. Usually you'll have to, finding out this value is not easy. You'll have to go around trial and error. So following that, we need to assign an array. So of unsigned 8-bit integers. So this is how you do it. 1 minute now. Yeah. So we call it tensor arena. we assign that size to. If anyone's not able to keep up, do let me know. So we create an array of this size, 2 into 1024. Okay then. Okay, so we should be doing that inside the namespace. So let's close namespace now. Okay, so what else have we got? We've made a tensor arena. We made a size. We assigned a size. Great. So next we have to do we made an array. So following that, we have the setup function, right? So let's move on to the setup function. So inside the setup function, let's see what we got. First, we have to set up an error reporter. So aside from that, before we get into that, we will do serial.begin for our LED before we get into the technical stuff. And pin mode. Pin mode, LED pin. Any guesses what would be here? It would be output. Just a standard LED, blinking LED, which we already gone over in week 1. And now we'll get over, we have to set up an error reporter. So we'll start with static. Static means it's remaining same. TF light, micro error reporter. Let's call this micro error reporter with underscores so we don't get confused the names. So now that we made this variable, we assigned a pointer. Remember, we assigned a pointer here. Error reporter is a null pointer of type error reporter star, a pointer to a micro error reporter. So error reporter equal to ampersand micro error reporter. So I think many people will be familiar with this ampersand. This is just to it shows that this should be saved. This is the pointer to the micro error reporter, which is basically the memory location or the address of the micro error reporter. Hope that's clear. So the micro error reporter actually provides a mechanism for logging debug information during inference. So we'll be calling it to print debug information, and the TensorFlow Lite for microcontroller, the interpreter will use it to print any error it encounters. So it will help in debugging basically. So then what we have next? So under the setup function, we've made up the set of the error reporters. Great. So next we have to map the ML model with get model function. So here's the model, sign model data CPP, which we made it under the collab notebook. So I've already made a pointer to the model. I've assigned a null pointer and I'll be defining it. Model equal to, so TF light get model is a function. This G underscore is a syntax for the get model. So our name is sign model data.h. Right? So we'll do sign model data. So now that we have a model, so here we imported schema generated.h. So this compares the model version with the standard version. So you need to do that because you always want to have a risk of uploading to your microcontroller and messing things up. So you need to always compare version before doing things because it'll be hard to debug unless you compare the version. It's a good practice to check the model version. So simple if statement will do. So to compare the version, we do model version. So we want to compare with the TF Lite schema version, which is the standard version. I think I'm going slow enough, but do let me know if I should slow down more. now, if the TF light schema version, so under this, if the versions are not matching, this obviously means unequal to. I hope everyone knows that. So you want our error reporter to report an error. So we set up an error reporter here, right? 1 minute, here, semicolon. We set up an error report here. Error report, this is how you call a class in C++. Report. So let's see what you want to report. Something like model provided is schema version. Hello. Yeah. Hello. Is my screen
Hello.
visible? Can someone confirm where I left off? Can someone confirm where I left off?
Sorry. Uh, I think it was bigger before this serial dot begin.
Oh, over there. Okay. So I'll just be doing this again then.
Yeah.
So now that we finish our namespace, let's go on to the setup function. So let's under the setup function, we need to set our first goal is to set up an error reporter. So so before we do that, let's do a serial dot begin, our serial monitor. So usually you want to do 9600 for an Arduino. This is the baud rate. For ESP32, this is the ideal value, the standard value rather. So when you want to do a pin mode, we define a constant integer here, LED pin 25. So I'm going to do LED pin and output. So here we just want to make an LED blink. So this is the standard part of that. So following that, we have to first set up an error reporter. So the way we do that is we do static TF light micro error reporter. So you want to name this variable micro error reporter. It's just the name of the variable. So here we did create a null pointer error reporter which points to the micro error reporter. So here to the null pointer, here I'll be assigning it. So error reporter is equal to ampersand of micro error reporter. Let me copy that and paste that here. So I think most of you will be familiar with what this means. This represents that this is a pointer to this variable. So basically this is the address or the memory location of this variable. So now that we've set up an error reporter, we have to map the ML model with get model function. So, 1 minute, yeah. What I'll be doing is I'll do model. We've already created a model pointer. So I'll be calling that pointer now. Model equal to tf light get model. And in that I'll be doing, so the name of our model is sign model data CPP. This was our output of our collab notebook, which Pratyush and Santosh covered. Right? So I'll be calling that model. So this G is basically to get model itself. So this is part of the syntax. Then you want to add this name, sign model data. I hope that's clear. So
Uh, Sanket, there's 2E in your sign.
okay, thank you. So now you have a model now. You want to compare versions. It's always good practice to compare version of your model. So otherwise, it's tricky to debug later if your model is not compatible. So a simple if statement will do. So here we include the library schema generated.h. Give me a moment. Schema generator.h. So we'll be able to call in that library now. So just to compare the model version. So we have a pointer model. So we do model version and we compare it with the standard version. So if it's not the standard version, it'll just we wanted to error to the error reporter to report an output that not rather than an output, it'll give a statement in the terminal that the versions are not matching. So we want to TF light schema version. So under this under the if statement, I just want to print an error. So we just set up our error reporter here, right? We just set up our error reporter. So we wanted to report an error. So we do error reporter report. One minute. Yeah, error report. So just a statement so we can identify the problem. So rather something like model provided is schema version percentage d. This is just a format specifier not equal to supported version percentage d. In that I'll just mention the specifiers model version and tf light schema. I'll just copy this. It's TF light. So I just close the packet here. I hope this is clear. We just compare our model version, and if it's not equal, I hope everyone understands this, is familiar with this. So if it's not equal, you want to just our error report to just report that the model provided is not equal, right? So just a model version being printed, and we're just printing out what are each other versions. So here it's not really necessary, but it's good practice to compare your model version before uh, deploying it. Okay, so what have we covered? We've mapped the ML model with get model. We've done the get model here. And next we've compared the TF Lite versions. So our next stage is to create an op resolver. Op stands for operation there. So what I'll be doing is static TF Lite ops micro all ops resolver. So here I'm using an all ops resolver to keep things simple. Otherwise, you would want to use a mutable micro mutable op resolver because that takes up less space. But to keep things simple here, and since this is our first TinyML application, I'll be using an all ops resolver. So I'll just call it resolver. So the all ops resolver knows all of the operations that are available in TensorFlow Lite for microcontrollers and is able to provide them to the interpreter. Okay, so I've created an op resolver also. So our next thing we have to go to do is build an interpreter. So the interpreter is the key part of a program which instructs the model to for the data. It extracts data from the model. So this is where all the magic happens. So first we have to declare a micro interpreter name interpreter. So I already made a pointer to it, name interpreter. So now I'll be calling that pointer. Hope that makes sense. So I'll do static TF Lite micro interpreter. So I'll call it static interpreter. So in that, the argument this take is our model, pointed to our model here. The resolver we are using, here we are using an all ops resolver. The tensor arena. So here is tensor arena is the array which loads the data of size 2 into 1024. And of course the site of the tensor arena, tensor arena size, just this variable, tensor arena size, and lastly the error reporter. This is the arguments which the static interpreter will take. So once you've defined the static interpreter, here you notice that we made a null pointer to the interpreter. So we just identify this with the memory location of the static interpreter. So we just interpreter equal to ampersand. Ampersand is a pointer to the interpreter. So static interpreter. I think I'm going slow enough, but do let me know if I should slow down. Okay, so I've built an interpreter. So my next goal is to allocate an area of working memory using allocate tensor. So this allocates the memory for our interpreter. So it's critical that we use allocate tensor because before attempting to run inference, otherwise the inference will fail. So for that we do TF Lite status allocate. We'll call the variable allocate status. We call the interpreter from the class. We call allocate tensor from interpreter class interpreter. I think there's been some spelling issues here. The thing about Arduino IDE does not give even squiggly lines to tell that there have been issues. So it makes it harder to debug also. So under the interpreter class, I want to call allocate answers. So this allocates memory. So here our memory size is an array of size 2 into 1024. Allocate tensors. Okay, so one more thing you want to do is you made this variable allocate status. You want to compare with if the TF Lite version. It's again useful to do that because it's a good practice to do that because it's hard to debug later if your the versions are not matching. So to allocate status. So if it's not equal to the standard version is KTF Lite 0K 1 minute. Let me just check this. Okay, it's KTF Lite. Okay. So if it's not matching, again you want to call our error reporter to want you. I want my error reporter to report an error. So simply a statement should do, which may help us to understand what the problem is. Simply something like allocate tensor failed. So if your version is not matching, I want to just simply return. One more thing I missed is over here also. Once you after you error report your error, you also want to return. So you're not wasting space. So just leaving some of the code. It's not doing funny things. Okay, so what next on our checklist? So we've allocated an area of working memory using allocate tensors. So next, under the setup function, I want to assign input and output pointers, right? So the thing about the keras is, okay, I'll show you first and explain later. I've already made two pointers of the type TF-Lite tensor. I've assigned a null pointer. Now I'll be calling those pointers. Input is equal to interpreter input 0. I'll explain the syntax of this in a bit. And similarly, output equal to interpreter output 0. So let me explain why am I doing this. So the thing is, the way keras accepts layer input, the value must be it accepts input in a 2D layer. So keras, which is a subsequent of TensorFlow, so it accepts input in 2D layers. So my input will be something like this. So for input 0, it will accept this a 2D array. Keras does this. I do not know why. So to call this number, to call 0, I do this input 0. So basically this calls the index 0 of my 2D array. So I just want to call out this number. So if let's not confuse us if it's 0 exactly. When input 5, we'll accept 5 as a 2D array. Keras does this. So this 0 is the index. So for this, I want to call out this number, right, as an input. This because this is entered through the CL monitor or anywhere. So to that, I do input 0. Hope that's clear. Okay, so we have also assigned input and output pointers. So we are ready for the loop function. So one more thing I want to do is Yeah. So one more thing I want to do is for our code here, I want to keep an inference count. I'll explain what inference count is in a bit. And not only that, I also should have, aside from the constant integer LED pin, I should have added a int inference count, but I'm not into the wheel. Inference count is equal to 0. The inference count should do. Right, so on the namespace, I've added constant integer LED pin 25 and integer inference count. This counts the number of inference. I'll be explaining what this is exactly in our code. But for now, I wanted to add on the namespace int inference count is equal to 0. Okay, so let's go back to our setup. I've added inference count equal to 0. I don't think that's actually necessary. Explain it 2 times. 1 time should do. So this is to keep track of number of inferences performed. Okay, so our checklist under setup is done. Now I want to go under loop. So our first thing under the model specific loop functions, I want to load data using input tensors. Right. So I want to repeatedly take load data under for a sine curve. So that's why I'm putting that under loop. So now let me explain you what we're trying to do here. So we want to we're not taking input from our CL monitor, but we are assigning an input. So for the I'll give you the variable first, so it'll be easy to understand. So I define a float position is equal to the static cast. I want to cast my cast. I'll explain you one bit. My inference count divided by static cast float, and I want to do k inferences per cycle. This should be in brackets. K inferences per cycle, right? And then I will define a float x value is equal to position into kx range. I'll be explaining this variables in a bit. Okay, so what we are trying to do here is we are assigning a so we are at the end we will have to do a analog right LED pin and assigning a brightness to that, right? So we want to implement the sine curve. So our inference count is the how many counts you're doing. So let us look at what kx range is. So notice that I have included constant.h, right? So let me look at constant.h. To define kx range as 2 pi, float is 2, 3.14159265359 for that is pi, right? So it's given a range of pi. So let's say our k inference per cycle, let's say it is I've assigned as 6. So what positions I'll be taking? I'll be taking 0 by 6 into 2 position into kx range, right? So 0 by 6 into 2 pi, 1 by 6 into 2 pi, 2 by 6 into 2 pi, and so on 6 by 6 into 2 pi, and then after that I will reset inference count to 0 moment it crosses k inferences per cycle, right? So that is just an example. So because we need to assign that brightness. So one case will assign 0 by 6 into 2 pi brightness, 1 by 6 into 2 pi, 2 by 6 into 2 pi, and so on, 6 by 6 into 2 pi. And once that is done, let me add that code now only. At the bottom of my code, I want if the inference count becomes greater than or equal to this k inferences per cycle, I simply want to reset back to 0. Okay. So I hope that is clear here. So now let's see what k inferences per cycle. Because notice that I have not made a variable here, k inferences per cycle, but rather I've included constant.h, right? So here there's a variable introduced, k inferences per cycle. Then basically number of inferences in your 0 to 2 pi cycle. So notice k inferences per cycle, I've assigned the value as 1000. So for each time you're looping, what will simply happen is, and you want to also increment this. So each inference. So each time I'm looping, this value is fixed 1000, and this is 2 pi, right? So each time I'm looping, I'll be doing 0 by 1000 into 2 pi. Next, so I'm adding this. I hope everyone understands this. It simply increments inference count by 1. So then I'll be doing 1 by 1000 into 2 pi, followed by 2 by 1000 into 2 pi, and so on. So, and I'll become 999 by 1000 into 2 pi, 1000 by 1000 into 2 pi, and moment it becomes greater than or equal to, I'm reaching it to 0. So I'm just looping. Again, it becomes 0 by 1000 into 2 pi, right? Because our model, if you remember from our model, it was only defined from 0 to 2 pi. First, we imported 0 to 2 pi, and then we found the sign value and added noise. I hope that makes sense to everyone. If not, do ask me. I'll explain again. Okay, so this will come later. Now I've assigned a float which represents the value, our input value. So I need to assign that as the input to our model. The way I do this is the standard syntax. So basically, I want to place our x value, this x value which is computed. I want to place our computed x value in the model's input tensor. So I need to convert that into tensor, and I want to place that x value into the model so it can compute the sign value of it. The way I do that is input. The input is this pointer here. In that class, I call data dot f0. It's just a standard syntax. So the input's initial value. I remember why I did this because the way Keras accepts input for input 5, it will accept a 2D tensor as 5. So to point to this 5 value, I do input 0. This is equal to x val, which is being computed here, x value. If I had only done this, I would get an error because this is expecting a 2D tensor, and this is not a 2D tensor, right? It's just a float. So I do dot f0. So let's see what we got next. Load data using the input tensor. That's also done. Next, what you want to do, you invoke inference using the interpreter. So now I'm asking the interpreter. So now I've loaded input. And now I'll be asking the interpreter to compute the output of this, rather the sign value of this. And I'll be taking that sign value into yval, another variable, which I'll be introducing later. Okay, so now I will instruct the interpreter to invoke the model. So to do that, I'll do tflight status invoke status. So invoke status, and I will be, so there's a class under interpreter, which I pointed up there under setup, invoke. So now I'll be asking the uh, interpreter to invoke our model to find the output of this input. I've loaded input, but I'm not now here. I'm asking it to calculate the output of it. Right. So one more good thing you want to always do is you want to compare versions. You do if so you do if invoke status is unequal to. So this is just good practice to do. Always do this, but otherwise it'll be hard to debug later. Find the cause of our issue. So it's always good to do this. Okay, KTF light. Okay. So now I'll invoke status here, which will not equal to this. I want our error reporter to give an error, to report an error, and I just want to return, exit the code, right? Reporter, I want it to report, or just a statement, something like invoke failed on X file. So I want to print that value, \n, which moves on to the next line. And under that percentage f is the format specifier. I want to specify I want to cast this X value. Let's do static cast the double. It's just for printing. You don't not much to do here. Now, rather than printing, I want to report an error xval. So let's take a look at this again. So if my invoke status is not matching with the standard version, I want to report an error. Report invoke failed on x value, and this value just been printed. Right. So now if it's not matching, I'll just return command code. Right. So now if it's matching, it will not go past it. If it'll just bypass it. Okay. So we're almost there. Now I've asked my interpreter to invoke. I've invoked my interpreter to find the value of our input, which is x value. So it has calculated the output because I asked my interpreter to do so. So now what I want to do, I want to access the output tensor. It has found the value, and now I want to create a variable which will access that value. Right? So now I want to read the predicted y value from the model's output tensor. Right? So I create another float y value. I'm assigning that as the output with data, no, output as a class data dot f0. So again, we are doing 0 because we this keras takes, if I didn't have this part, this would be a 2D tensor, but y value is just a float value, which is a 1D tensor. So I index it to 0. That's just the way keras does things. Okay, so our checklist is ready. I've accessed the output tensor also. Now I just want to, now I have my sign value, and I want to instruct my Arduino to make the LED blink accordingly. From here, I think everybody should be familiar with what I'm going to do. So just to compare, this is our output data, our model's output. Let's find the value, float true value is equal to sign. Sign is the mathematical sign of x value. I'll just be showing how accurate our model is. Okay, and then just some serial prints on our monitor. Sign off. Just write it the same way, the way I'm doing it. So it'll make sense later. Serial dot print. I'm going to print the value of x. Sign of what we're doing. X value. Followed by serial dot print is equal to. I want to close the quotes. Then I want to print the true value. It's just way of specifying so our CL monitor looks cool. Nothing much is happening here. I'm just printing stuff on the CL monitor. Then serial.print \t. \t just moves it by a tab. \t predicted. \t just moves it by a tab. Predicted value is y value. Serial dot println y value. This I'm just printing out data, nothing much. So it will be helpful for us to understand how well our model works. So finally, now I just need to create another variable, maybe something like int brightness. So I'm sure you guys are familiar with GPIO pins and PWM pins. So in a PWM pin, it can give analog output. So in an ESP32, most of the GPIO pins are PWM pins. So in Uno, there are only a select few PWM pins. Okay, so I want to cast it in. I want to do y value is the sign of, right? Sign. So it's from 0 to 1. And notice that hex code is from 0 to 255. So this is just to assign the brightness. 255 into y value. So this from 0 to 1, right? Y value. So 255 times that will be from 0 to 255. I want to cast that as an integer. And I also want to put an absolute here because negative will not make sense. So let's say we're having a sign of minus 30. Sign of minus 30, negative half. So I'll have a negative input here. So I'm just doing an absolute value here. It's just a standard function. And now that I have brightness, I'm just doing analog, right? I hope everyone understands this part because it's already been covered. Brightness. Okay then. So now I'm assigning my brightness. I'm asking it, and now I'm asking to increment the count in my next. So as it repeatedly loops, it increments count from 0 to 1000. And moment it crosses 1000, the brightness will be what? Y value will be x value will be 1000 by 1000 to 2 pi, right? So y value will be 0. Brightness becomes 0, and I'm assigning a moment it crosses 1000 greater than equal to 1000. I'm making inference count back to 0. So it again loops from 0 to 1000. Does everyone understand this? I hope. To let me know if there's any doubt. Okay then, so our model is ready to upload, right? So I will be compiling this and uploading this. I will turn on my camera once it is uploaded. So I understand that many people don't have hardware here, so I thought the only way I can do justice for that is I'll show the output in front of my cam. So let's compile this. So it's always before uploading, it's always good practice to build first, because so you know how much place your model. Whenever you're working with models, you want to build first, so you know how much space it is taking. I'll explain you in a bit. So it's likely that I have an error somewhere here because some spelling typo or something. Because Arduino ID does not even give squiggly lines, so it's hard to say when there's a mistake. So let's wait for it to build. Meanwhile, if there's any doubt, you are free to ask me. I'll try my best to explain you. Meanwhile, what I'll do is I'll just go over to and show you that we've covered everything. So what I want to do, I'll include library first. I want to go to variables. So under variables, I want pointers to my model. I'm assigning for now all of them as null pointers. It's done. To my error reporter, to my input and output tensors, and I want an interpreter, which is basically the magical part, which instructs my model to perform tasks, right? So, and I've already made an interpreter, right? So, and after that, I want to assign a tensor arena size and an array. So, on the setup, so I want to set up an okay. There is an error here. This should be TF light. See that whole thing? There should be probably some typo here. Are you guys with me? Am I audible? Just to confirm.
Yeah, you're audible.
Yeah, so on the setup function, I set up my error reporter here, and then I map the model with the get model. I compare the versions. It's always good to compare your version. I create an op resolver. Here I'm using an all ops resolver, which generally takes more space, but to keep things simple, since it's our first application, I use an all ops resolver here. But usually you don't want to use it because this takes more space, and you want to minimize space because your microcontroller has very limited RAM. And your ESP32 itself has like 4 KB RAM. Then I want to build an interpreter here. So interpreter which instructs the model to perform tasks, right? So I build my interpreter and I allocate area of working memory using allocate tensors. Before that, again, I'm comparing versions if my allocate status is fine, if it's okay. So I allocate memory. I call allocate tensors. Give me a moment. I'll have to plug in battery. 1 minute. Okay, so I've allocated memory. Now I'm assigning input and output pointers, right? So again, I think I've already gone over many times why I'm doing this input 0, because Keras accepts input in terms of 2D tensors, but our input and output are simply floating values. So input 0 will, there's a error here. Let me check. It says if okay, there should be a semicolon here. Let's continue building that. The other thing, what Arduino it never tells you you're missing semicolons or something. It doesn't tells you about error before building it. So likely to get errors. So I've assigned input and output tensors. And then inside my loop, I've load data using input tensors, and I've invoke inference. I'm asking it to invoke. Like I'm instructing the model, our interpreter, to task to instruct the model to find the output of this. So our model will find the sign value of this. So once that is found, I'm assigning a output tensor to access that value. Output data f0. This is a bunch of uh, just this part is just printing on my serial monitor. And finally, I'm assigning a bright and integer variable which are used to assign brightness. An analog right LED print brightness. I hope it's clear to everyone. We'll wait for this to compile. I'm missing a semicolon here. One minute, I'll fix this. Okay, I don't know what the error was. I just added the semicolon. I will run it again. Okay, until it builds. So as I was saying, you always want to build first before you start compiling, before you start uploading. The thing is, you're working with models here, so you need to know how much space it is taking, right? So if you don't know how much space it is taking, you might be messing with your microcontroller. So once your model is built, it gives an output space. So if it is ideal, then only you want to upload. You don't want to upload before. Don't want to upload directly. So you want to see how much space it takes up, and then you want to upload. I'll show a demo. I'll show a demonstration here. It will give me a statement saying this much space has been taken up. So until it compiles, do you guys have any doubts? Sonata. So obviously it'll take time to compile out because we're importing a model here. So it will take time. Give me 2 more minutes. Okay, that's finished building. I shall show my screen. Yeah, take a look. So our sketch uses 28% of a program, so which is safe enough to upload to a microcontroller. You always want to check this before because we are working with the model here, which you are optimizing. Here I'm giving you the size of a tensor arena. So usually you want to do trial and error and you want to minimize this. Okay. So it is 28%. Now I'm ready to upload it. And I'll turn on my video to show you an output. Right now, into my ESP32. Okay then. So it has finished uploading. So I will show you guys the output. So as you guys can see, let me turn the light one minute. So if you observe the LED here, so it is implementing a sine curve, right? So it goes off and it stays on for a while and turns off, right? So if you want to further see the sine curve, because it's hard to say. Like I showed you the LED implementing a sine curve, but how do you know it's a sine curve? I'll show you that. One minute, I'll give you proof that it is a sine curve. Right, so let's take a look at the serial monitor. See, let me pause it. Let's see how well our model is fitting. This is the actual value here, true value. We've printed out true value, and this is our predicted value, 0.5 to 0.53. Sine of 0.60, 0.58, and our model predicts 0.55, right? So we can go to negative values. One minute. You can see how well our model is holding. The minus 0.59 shows minus 0.64, which is more than 90% accuracy, which is good enough for what we are trying to do here. Because we're only making an LED blink, a glow, according to a sine curve. If you want to see the sine curve, let me show you in the serial plotter. See, this is a sine curve. It's from -1 to 1, and you can see how well our model is implementing a sine curve. So you see the two lines here. The blue is the actual sine value, and the violet is what our model is predicting, right?
Sanket, we can't actually see Sanka. I think you have only shared your tab.
You can't see. Okay, one minute. Can you see the serial monitor? Hello.
No, not.
Okay, give me a moment. Okay, can you guys see a serial monitor now?
Yeah.
Yeah. So this is our model here. I paused it. So let's see how the model is holding. Sine of 0.7. This is true value, and our model is predicting 0.61. Right. Let's see what we printed here. True value and predicted value. Right. So sine of 0.81, 0.72, and our model is predicting 0.71. So our model is pretty accurate with 90% accuracy at least. If I go to the negative side, minus 0.78, our model predicts minus 0.72. So our model is doing pretty well. Now, if you guys want to see the sine curve, right, I'll show you. I'll go to the serial plotter. Can you confirm if you can see the plotter?
Yeah, we can see.
Yeah, so now you can see the sine curve being plotted here. So this is the proof that our LED is implementing a sine curve, and you can see how well our model is holding. The blue line is the true value, and the violet line is our model's prediction. So you can see how accurate our sine curve is, right? So
Yeah.
I believe that's all from my side. So this was the last session. Thank you all for joining. Is there anything else to be said?
Hope you guys enjoyed this
Hope you guys
TinyML
enjoyed.
arena.
Yeah, Pratish, why don't you share that last slide then?
Huh? Oh,
Yeah.
So hope you all enjoyed.
actually, Sanket has last slides.
Come again, sorry.
Okay,
Wait a
give me a
minute.
second. It's fine. Yeah.
So this is the last session for week 3 of implementing a sine curve. So that's all from our sides. If there's anything else, you can send me on WhatsApp.
So
Our
guys,
team worked a lot for this. So
yeah, this was our team.
Yeah, these are the our guards who've conducted all of the sessions for you guys. So, yeah, huge shout out to them. And yeah, thanks for joining. If you stick with us till the end, so if you attended most of the sessions and uh, finished the tasks, then you'll be receiving a certificate from us soon. And yeah, just check out our Instagram page, Electronics Club IITM. You can share with us any projects you've made. We'll give you a shout out there as well. So yeah, we have a feedback form. Why don't you guys just go ahead and fill this and share it with your friends who have attended the sessions too, like whoever's there here. So I'm sharing it in the chat. Yeah.
okay, Suresh, you can go ahead.
Brother, this group will be terminated after this session completion of after 24th, or it will be continued.
This is the
Group.
last session.
It's okay, but this group will be
Oh,
continued, or this group
There's
will
no
be terminated.
talking about the WhatsApp group.
Ha ha.
Yeah, there's no purpose of the group. If you want to leave, you can, but it's probably not going to be.
So
Yeah.
if I want to join this electronics group, so in core team, so is there any possibility to join?
I'm sorry. Which like which department year are you from?
I am from electronics and instrumentation division. I'm tech electrical engineering.
Okay. All right. Fine. So yeah, you can definitely like attend whatever sessions that we conduct and participate in anything that we have. So yeah, we'll share whatever information regarding the club on the WhatsApp groups that we have. So if you want, you can stay back in the group and just like check out any updates. That's fine.
Oh, okay. I will save your this admin of the contact number, and I'll approach personally to you guys.
Yeah. Sure. Okay.
Okay. Thank you. Thank you.
Yeah. Anyone has any other questions, you can ask, or else we can end the session.
I guess there are no questions then. So we'll end the meeting.
Okay. Yeah.
Thank you all for joining. Hope you guys had learned something new. Bye.